Bonjour. Aujourd'hui, notre intervenant est David Corfield, qui est l'auteur d'un livre qui s'appelle Towards a Philosophy of Real Mathematics, c'est-à-dire vers une philosophie des vraies mathématiques, un titre assez polémique à l'époque. Mais c'est quelqu'un qui est parfait pour ce séminaire, qui va être en anglais. Et vous avez le titre là, c'est un séminaire sur le sujet de la théorie des catégories.
Okay, well, thank you very much, everyone, for coming. Good to see you all, and thanks a lot to Tim for inviting me. We go back a little way. We actually were on the same undergraduate course, the same college, too long ago to mention. Slightly less far back in time, I was in Paris. I was interested, after mathematics, I was interested in psychoanalysis. And it was during that phase in Paris that I started to fall in love, is that the right word? Fall in love with category theory. So I was intrigued to see that last year, Alain Conn has come out with a book with a big bold claim, talk about applications of category theory. The unconscious is structured like a topos. Okay, where a topos is a certain kind of category. He's appealing quite clearly to the writings of Jacques Lacan, who told us that the unconscious is structured like a language. Okay, we change one word language to topos here. Okay. Good. So as I mentioned, even further back in time, I was studying mathematics, so I was very interested to follow Tim's career, as he did so well, progressed from being an undergraduate together. I was kind of intrigued then when he wrote an article, I'm not quite sure the date, I think it's around about 20 years ago, perhaps you can tell us, called Two Cultures. I found it on the internet, it didn't have a date attached to it, but I think it's around, somewhere around about 20 years ago, which was quite intriguing to me because he just won this most prestigious prize, and the article spends some time sort of almost defending his style of mathematics. He's talking, so there's an allusion here to the writer C.P. Snow, who had been concerned that there were two cultures, a sort of scientific culture and a humanities culture, and they didn't really speak to each other, and it was seen as very important that you be aware of the one culture, particularly the literary humanities culture, and you could be ignorant of science. And C.P. Snow was very worried about this. So Tim is telling us that there are two cultures within mathematics. They're the theory builders, and we can think of some big names, people like Grothendieck and the revolution in algebraic geometry that he performs, people that work on the Langlands program, and so on and so forth, as contrasted with what he called the problem solvers. So this is clearly his area, combinatorial graph theory. And he makes this comment: one can almost imagine a gathering of highly educated mathematicians expressing their incredulity at the ignorance of combinatorialists, so his side, most of whom could say nothing intelligent about quantum groups, mirror symmetry, Calabi-Yau manifolds, the Yang-Mills equations, solitons, or even cohomology. Okay, so, I mean, rather noticeable choices there are things very close to mathematical physics. And in this epoch, there was a very important work going on in the interface between mathematics and physics. If you think of Edward Witten in conversation with Michael Atiyah, that kind of world, if you know what we're talking about there. This was very important cutting-edge mathematics that was taking its inspiration from physics at the time. So many of the topics being mentioned there concern that subject. Yeah, interesting that he mentioned cohomology on the end here. So, I mean, category theory begins in the 1940s, and it's very much constructions like cohomology that drive the invention of category theory in the hands of Sanders MacLean and Samuel Eilenberg. Okay, so it's very much, category theory is very much on from this other culture, the theory building culture. Okay, and what are the problems they're dealing with? They're interested in these phenomena where one will have some kind of collection of, say, spaces of a kind, and then we're going to assign to these spaces some algebraic entities of some description, and we're going to use this mapping from spaces to maybe groups or something like this. We're going to use it to solve some topological problems. Because, for example, there could be, I'm interested to know whether two spaces are homeomorphic or not, and if this assignment sends them to different algebraic objects, I'll know that they must already be different. They must not be homeomorphic back here. But they're trying to get at this consistent, systematic assignment of one kind of mathematical entity to another. Okay, so again, it's kind of intriguing. I always meant to have a closer look to see, can one characterize the disciplines where category theory gets a very strong grip compared to other parts of mathematics where it has much less of a grip. So because historically algebraic topology was right there at the beginning of it, Grothendieck and algebraic geometry. But you could be working on something like the Langlands program, and you just can't get going without some understanding of category theory. It seems to be spreading perhaps further into other areas of mathematics. This is, I think, Michael Harris, perhaps some of you know him. He was a mathematician here for many years, American mathematician, but went back to Columbia. Here he is writing to me. He was kind of fascinated to see there's a course being run by Clausen and Scholze. And he wrote to me, "Some time ago I expressed skepticism regarding the possibility of recovering hard analysis categorically. I'm still not convinced, but it seems soft analysis is already there in this summer's course by Clausen and Scholze." And if you look into, I'll put these slides on the web if anyone wants to follow things up. Anything in blue is a link off to some other document. So you can find Clausen and Scholze writing there. "We would like to say that our proofs are proofs by formal nonsense, and in particular analysis-free." So anything, when you hear anything to do with nonsense, it's usually associated with category theory, as though it's a sort of abstract nonsense. But it shouldn't be seen in, well, some people do use it in a detrimental way, but I think many people don't use it in a detrimental way, with the idea that it's sort of absorbing so much of the structure that you need in a certain situation, that it's making life easier for you. It's taking out what should be the straightforward stuff. It's abstracting that from the work you're doing and leaving you then with the particularities of the situation you're dealing with. Okay, so I'll work on the assumption, I'm sure that many people with profound knowledge of category theory, but I'll take it that people here don't have such a knowledge of category theory. So I'll spend some time explaining a bit about what category theory is and then talk a little bit about applications. Okay, so what's one doing? What were Eilenberg and MacLean trying to do? So they had got a collection of entities, some kinds of topological spaces, but you don't just collect them in a big heap. You want them to be related to each other by the right kinds of mappings. Maybe something like continuous mappings. So we have a category of objects. These objects in this case are topological spaces, and then the arrows, the morphisms between them, are continuous maps. Okay, so then once we've got one of these categories, we then want to map or to send this category to another category. There may be somewhere else there's a category of groups. These algebraic entities, groups, and their homomorphisms as arrows. And now we want to send one category across to the other category. Systematically, in such a way that it respects composition, for example. So if I've got two arrows in my original category, one arrow followed by another arrow, these compose to complete the triangle, so that when I map this across to my target category, that the same composition holds over there. Okay, in the second category. Okay, so I'm using a functor to do that. A functor will be sending one category to another category, and then I might think, well, I've got two functors. I've got a category C and a category D. I've got two functors from C to D, and I might want to make a systematic comparison of these two functors. So I need a sort of a next level arrow, an arrow of the next level, a sort of a two arrow, not just a one arrow, but a two arrow that relates those one arrows. And these things are called natural transformations. Okay, then I might also, if I've been sending my category across to another category, I might want to find something coming back in the other direction. Now, very rarely will it be the case that I find a perfect inverse coming back. Well, only, of course, if those categories were equivalent, could I do this. But if they're not, and obviously like topological spaces and the category of groups, they're of course not equivalent. But I may be able to find functors that come back in the other direction. And I can sometimes find the best version of this coming back, which are called adjoint functors. And this is very much at the heart of category theory. You're looking for adjunctions, adjoint functors, wherever you go. And once you have these things in place, you can understand all sorts of things like enormous number of dualities that appear in mathematics can be understood from this point of view. Okay, and we have dualities going back, right back to projective geometry in the 19th century, but all other kinds of dualities, stone duality, and so on and so forth. Okay, and they can all be captured in this way. So we're trying to get at this very sort of systematic approach to finding really these kind of common structures that are appearing all over mathematics. Okay, and a final thing one might want to do once one has one of these adjunctions, if you take the original functor and you come back, you compose it with the adjoint coming back the other way, you construct these things called monads and comonads. Okay, and these are going to be kind of important. I mean, some of the applications that we'll see later take place in computer science, where we find monads and comonads of great interest. Okay, okay, not all categories are the same. Some categories come with a particularly interesting structure for you. Often, I mean, an important structure involves these limits and co-limits. So you can have a category, for example, that has a terminal object. This means it's got one of its objects is such that there's a unique arrow into that object from any other object. Well, and itself, of course. So if you want to think about the category of sets, this would just be a singleton. A singleton would just receive a single arrow from every other object, and so on and so forth. I mean, products are, as one might imagine, so in sets, it's just the Cartesian product of two sets, just pairs from each of the set, and co-products are going to be disjoint unions, and so on and so forth. Co-equalizers are kind of picking up on the idea of an equivalence relation, quotienting out to an equivalence relation. Okay, so again, they're very familiar. And pullbacks are sort of like intersections and so on and so forth. So the kind of constructions that are very commonly encountered, and certainly encountered in the category of sets. And you're wondering, do these things exist in the particular category of interest to you? And just to show you, it could easily not be there. If you think about a category of smooth manifolds, I could have a smooth manifold there. I could have two submanifolds, so they've got these injections going in from a pair of manifolds here going into the main one. So the pullback will be picking up the intersection of those two smooth manifolds. And there's no reason for the intersection to be itself a smooth manifold. Okay, so the category of manifolds, smooth manifolds, and diffeomorphisms doesn't have pullbacks. Okay, and this might be a problem to you. You might think, I don't like this category. I want to improve it, perhaps. And then we get these very general kinds of results of this form, so that if I have an adjunction between two categories, one and another, a left and a right adjoint, the right adjoint will always preserve all the limits in the original category, and the left adjoint will preserve co-limits. So you can see that in practice. So here's an adjunction. If you have the category of topological spaces here, and we've got the category of sets over here, then there's a functor which takes a topological space and just yields its underlying set. And there's functors, well, in fact, in this case, there's functors on both sides, but there's only one that's coming back from the category of sets, and it will deliver a topological space over here with a discrete topology. Okay, they're adjoint maps to each other, so that as the underlying set, there is a right adjoint. It should be preserving the limit structures on the category of sets, so in particular products. So the underlying set of a product of topological spaces is the same as the product of the underlying sets. Okay. And I don't have to keep proving it, that's the thought. I don't have to sort of keep proving it for spaces and groups and so on. Anything that looks like this, the same result will apply. Okay, so there's Alain Conz was telling us the unconscious is structured like a topos. So here they're appearing here. So they're a special kind of category. So very, very nice in a sense. They got a lot of very pleasant structure to them. They got kind of just about all the limits and co-limits that you would want. So the category of sets and functions is a good example of this because it has all the small limits and co-limits. Okay, but there are other, this is due to Grothendieck. Grothendieck discovers that there are categories that have very similar properties to the category of sets in having these limits and co-limits, but which aren't set. And these things are known as toposes. So it may be possible even, as I say, you may be working with a certain category and you may want to improve it in a certain sense by this construction. So what is that? So we had our category, COP, well that's just me taking the category and reversing all the arrows. And then I'm looking now at so this is going to be a new category that's going to collect together functors from the COP into the category set and then have natural transformations as its arrows. And the very act of you doing this sort of upgrades your original category into something that's now going to be a topos. And now it might be easier for me to work here. And you can show that there are elements, it really is an embedding, because there are elements in this thing on the right here which are behaving just like the objects of C. So they're just carrying on their business as they were before. They're just now in this much more generous setting where I can do a certain kind of reasoning. So you get this kind of slogan, it's better to have a nice category of objects than a category of nice objects. It's better to have, even though you may be thinking, well, I got some strange creatures in here, I got some strange things which are functors from COP to set. Did I really want to be talking about those? But they're now in my big topos, my pre-sheaf topos here. Yeah, I mean, of course, there's a whirlwind of many, many decades, but you know, the big story, perhaps, of the last, well, how many, 20-odd years, maybe, is the shift in category theory to infinity category theory. Okay, so now I'm not so much, I've got my objects, and I'm now not so interested in just a set of arrows from one object to another object. Maybe I've got something like a space of arrows from one object to another. And if I'm in the world of anything spatial, it's quite likely I've got a kind of space of morphisms from one, or arrows from one object to another object. So that isn't just a structure of a set now, it's got a higher structure to it. So these infinity categories, they're trying to pick this up. They're thinking there's this deeper internal structure to the morphisms, the Hom sets as they're called. So instead of Hom sets, we've now got these Hom spaces. Okay, now a lot of useful constructions are now possible in this setting. So this is very much sort of Jacob Lurie working, where's he now, in Princeton, isn't he, IAS. That kind of person who writes these enormous books on infinity category theory. Okay, as the setting, the right setting for modern geometry, well, and modern algebra, I suppose, too. Okay, but the limits and the co-limits are working just very well for that kind of world. Yeah, but they're also, somebody, well, I'm going to be mentioning somebody that I've worked with, studied for a long time. That blue link is going to take you off to an article of his where he's saying, and these things are just the right place to do modern physics in. Okay. It's not just, you know, the mathematicians off on, you know, whatever strange pathways take them away from their original settings to look at these infinity categories. It's actually in the very nature of physics itself to need exactly these sorts of spaces. Because how do we understand a space? Well, we understand it by the way it's probed, by the way that things map into it. So we're looking for sort of collections of probing objects, and we're saying, so rather than just the probe object itself, we want to know the ways in which the probe object can be mapped into some other object. So an object is defined by the way it's probed, well, I suppose would be the slogan that comes out of this. Okay, all explained very nicely in that article that's linked there. Okay, but we're all about, again, improving. It's just like we had the story of improving a category into a topos. Again, we can improve an infinity category into an infinity topos. Okay, and we'll see perhaps why you might want to do that. Okay, so let's backtrack a bit. So we're supposed to be heading a little bit towards applications. So it was realized fairly early on that it's not just mathematics itself that where we find these patterns picked up by category theory. That we find them in logic itself. Already in logic, we are finding these patterns. So, you know, I mentioned before we could collect entities of a certain kind, and we certainly collect together sets and their functions, or we collect together manifolds and their diffeomorphisms and so on. But nothing stops us collecting things which don't really look like that. So we could collect together propositions. We could be dealing with logic. We could want to deal with the collection of propositions. And now the arrows here are going to be entailment relations. Okay, so if A entails B and B entails C, obviously A entails C. So we get the composition working nicely. And then you start to notice, oh, wait a minute, what about this? This is something close to the deduction theorem. If B follows from both C and A, then from C we could deduce that A implies B. And I mean, naturally enough, you kind of wanted to, you know, when you see this, you kind of know at stake is something pretty close to what's going on between multiplication and exponentiation. There's something sort of similar going on here if you think about it long enough. Yeah. But here we found it, we've located that structure precisely in just a simple propositional logic. And just to check that things work, so this thing is now set up as an adjunction. It's precisely the way adjunctions work. Okay, so we've got our category of propositions, and we've got two functors. One functor is conjoining A, and the other functor takes a proposition and takes a proposition like B and sends it to A implies B. The entailment from A. And this is now set up nicely to be an adjunction between these two. So that C and A entails B if and only if C entails A implies B. And just to check it's all still working nicely, because it should be. So B and C, for example, is the product in this category of propositions. I'm suggesting to you that this thing here is a functor. A implies blank is a functor, and it's a right adjoint. So it ought to preserve products. So it ought to preserve this product of B and C, and you're seeing it does here. So A implies B and C must be logically equivalent to A implies B and A implies C, yeah, which it is. So that's reassuring that the right adjoint has done its business and preserved products here. Or taking it up a step, so this was known into the late 60s, 69. William Levere comes out with, sort of sees that there's categorical structure in first order logic. Okay, so when you're learning first order logic, you might have this in some sort of introduction rule for the existential quantifier. I mean, if you could reason from some general X, that because it's got property P, therefore some other proposition follows Q, you'd know that if you actually had, if we could prove there exists X, such a P of X, then Q would follow. Okay, and again, we can see this as an adjunction. Now it's the existential quantifier is there as a left adjoint. It doesn't look like much has happened on the right. In a sense, something has happened on the right. The Q coming back the other way is now in a world where there's this variable available. The X variable is available to you, but you're not seeing it marked. But it's as though it's like a constant proposition in a space of variation over X. So that was the kind of secret mapping that's going on as the adjoint. Okay, and just to check this was all working still. This existential quantifier I'm saying is a left adjoint. It should preserve co-limits. It should preserve co-products, for example. In this world of these so this thing is a co-product. The co-product of these two predicates, R and S, is R or S. Okay, the V shape is an or. So left adjoint should preserve this, which it does. Okay, the right adjoint wouldn't have worked. If it had been for all X, Rx or Sx, it wouldn't have preserved. That's not the same as for all X, Rx, or for all X, Sx. Okay, but there is another one. Of course, the universal quantifier will preserve the same setup if we had the conjunction, not the disjunction. Okay, so category theory starts finding its way into logic, and through the 70s, maybe people can't find jobs too easily, and they end up in computer science departments, or for whatever reason, there's suddenly a lot of input from category theory into computer science. The cutting edge of work along those lines would be the foundational theory called homotopy type theory, which has kind of been in existence for maybe 10 to 11, 12 years now. Okay, so it's presented as this new foundational language. We don't need to say that really the only foundational language is set theory anymore. We have an alternative. And it's intriguing. I think it should be intriguing for philosophers because it's a very structural theory. You can't, in some sense, you can't express non-structural things in this language. Okay? Because anything you can say about one entity, and if there's an equivalent something about a type, if you know you have an equivalent type, you can transport everything you say about that original thing across to the other thing. Okay? So you just can't write in a non-structural way in this language. Okay, and a lovely slogan. So we've got those things, those clever geometers are doing, people like Lurie, these infinity toposes, these very, very nice frameworks in which to do modern geometry. And then we've got this new language, and it's the internal language. I won't say much about what an internal language is, but still, it's of the flavor that anything you prove just using homotopy type theory can be interpreted within any infinity topos. I can take a little piece of reasoning in homotopy type theory, and it translates into any infinity topos. So I can get lots of different results for free, if you like, just proving something once, which again is a very category theoretic way of going about the world. You're trying to save time in some sense. Yeah, and I think, this is less philosophy of mathematical practice. I think just, if you're interested in English, Anglophone philosophy, there's a lot of work you could redo using this new language, I claim in my book, philosophy of language and so on and so forth, that could be done through this new foundation, rather than the old predicate logic and set theory, as has been the case for so very, very long. Okay, so yeah, we start, so as I say, we had category theory, we find a connection through to logic, then into the 70s we're getting a lot of people working on computer science and category theory. So it certainly was important that there were people thinking about computer science. That has led up to this modern development of homotopy type theory. Because you're trying to, there was always a link between computing and constructive mathematics. Okay, because you want a program to perform a task, you want something kind of concrete. If I tell you that all collections of entities, you can find a such and such a largest element or something like that, I don't just want to know that that's the case, I actually want you to give me an algorithm. So I give you a collection and you give me back the largest element. So I construct it. By the very act of proving something to be the case, I construct something. I produce a function, say, or something of that kind. Okay, so this is really tightly woven in with a computer science outlook, particularly these functional programming languages. And those things I mentioned at the end of the constructions of category theory, I mentioned these monads and comonads. So these now find their place in this system. Because if you just treated a computer as performing, just carrying out, conducting the application of functions, well, nothing would come out. You'd give it an input, you'd press a button, and it would just do its business, and it would stop. Okay, but you don't want a computer just to do this. You want the computer to do something like print the answer. You want it to change the world. You want it to send a signal down to the printer to print the answer. Okay, so this isn't modeled. So when I press the machine again to apply another function, I've got to, what am I doing? Was the output really whatever was going on in the computer plus the printout? Is my new function when I apply it, is it just applying to the thing going on in the computer? And these monads and comonads were used, so monads are trying to capture the notion of effects, okay, where your program has effects on the world, it does stuff out in the world. And the comonads are modeling the way that the program can use resources from outside, extra resources from outside. So, okay, so it may require the person using the program maybe to press a button at a certain point as the program's running. And there needed to be a way of capturing this extra input. Okay, and so monads and co-monads are doing this. And we get such a tight connection that people started joking. There's a bit of a battle as to the term used. Somebody wanted to call it Trinitarianism, with an allusion to theology, as though if you've got three aspects of the same thing, three aspects of God. Now here we've got three aspects of the same thing, and they're appearing in from the point of view of computer science, and also from the point of view of logic, and also from the point of view of mathematics. And this computer scientist called Bob Harper was famous for sort of saying that you've got something good if whenever you have a new concept that it makes sense in all the three disciplines. Okay? If you've got a construction and it makes sense in all three disciplines, you have an important construction. Okay, so we get these tight tangles, computation and spaces and logic. Somebody else didn't like the Trinitarianism, has called it trilogy, but I'm not sure it's quite a trilogy. It's not in the sense of three separate books, it's the three versions of the same thing. Okay, physics then also has to come into the story from the 1980s. That kind of collaboration I mentioned between Atiyah and Witten gives rise to people working on these topological quantum field theories, which are expressed precisely as functors. Okay, now these functors are now going from categories of manifolds. Where now actually the arrows are kind of more interesting in a way because the arrows themselves are spaces. So famous example, well, the Americans say pair of pants. I guess if you're English, you're going to say pair of trousers. Anyway, you've got kind of one hole here, and you've got two holes over here. And imagine a pair of pantalon. Anyway, in between. And it's the arrow there is the actual space that goes between them, which has as a boundary the input and the output. Okay, so this is going to make up a certain kind of category because I can now, the other end, I could get another pair of trousers the other end and glue the ankle holes together, couldn't I, and generate a bigger space. Okay, so we've got that kind of world. So this is the subdivisions of space-time for the physicist, and then we're assigning some kind of algebraic entities to the boundaries and also to the processes that take place, the spaces in between. Okay, they're often choosing something like category of Hilbert spaces, say, and linear maps. Okay, and people started noting, well, it's kind of interesting because both these categories that are being mentioned here, the product, this isn't the product like you got in set. When you gave me a product of two sets, an A and a B, so they are represented by pairs, aren't they, of A and B, it's easy to project out onto one component, the first component or the second component. In this world, the products available don't do that. They don't behave like that. And that's very famously caught up with the issues in quantum mechanics that if I have two quantum systems and I entangle them, a state of the entangled system is not just a pair of a state of the first system and a state of the second system. Okay, there is some superposition, there is entanglement. Okay, so both these categories sort of share in this way of being non-Cartesian. So this gave rise to a lot of kind of interesting work. Well, this is kind of interesting. So there's a kind of cutting-edge stuff that comes out of Atiyah that goes down quantum topology and a lot of the kind of work that gave Edward Witten his Fields Medal, trying to understand the way that knots work. Another line sort of tried to abstract away, trying to work out what was the very, very basic bare bones of what's going on in a quantum theory. And they, at the same time, gave a diagrammatic way of representing what was happening in these kind of monoidal, non-Cartesian kind of categories. And you see, diagrams, these category theorists just love these diagrams, these string diagrams as they're called, that represent the morphisms going on inside their monoidal categories. And two fairly recent books are trying to distill the absolute essence of the quantum situation. So this Bob Kirker, he's gone on, he's working in a private company now that deals with trying to get at quantum computing. They're trying to develop quantum programming languages. And they find very helpful this diagrammatic notation they use. Owes a heritage even back to Penrose in the 70s, trying to do his work on tensor calculus. Okay, so to date we have, I mean, of course, the first applications of category theory are to mathematics itself from the 40s. Then we start to see it being applied in logic and foundations through the 60s, and the computer scientists join in the 70s, and the physicists through the 80s, such that, I mean, another good friend of mine, John Byers, that we, well, I'll mention later, we ran a blog together for many years, wrote a paper in 2009. He's saying it's not just the case that you've got Trinitarianism between logic, computation, say, and topology, something sort of mathematically spatial. There's also physics as well involved, and it's category theory that's speaking to all these four. It's providing the same language which will allow for the same, it's exactly the same phenomena are going on in these different fields. So this is from his 2009 paper with Mike Stay. Yeah, for example, you know, parallel processes going on in physics is going to be connected to disjoint unions of cobordism, so that's spatial stuff passing through, which is the same as proofs being carried out in parallel, and so on, which is the same as programs being executed in parallel. So no entanglement going on here. Okay, so he calls it the Rosetta Stone because, of course, you're supposed to be like interpreting Egyptian hieroglyphs. You're supposed to work out from an element, from an entry in one column, what would be the equivalent in another column. Okay, and this line of work carries on and is doing really intriguing stuff. So some people I follow closely, this program of Satie and Schreiber, and right up to the construction of a candidate. So the idea was to unify the different string theories under a thing called M theory, and they have a proposal for what this M theory should look like. But it's wonderfully woven in with these new foundational languages. Okay, they're really trying to get the kind of foundations of mathematics to speak to the physics. Okay. Yeah, and it's not just, I mean, you know, the famous line is ask a mathematician about the axioms of ZFC, and perhaps we should try that. And often they can't tell you all the axioms of ZFC, is famously, because it's not really having that close a bearing on the work they're doing, on their constructions. Okay, but here we seem to have a case that goes against this, because very much, I mean, I've seen it, I've seen them doing it, so I know they do it. So they're taking these extensions of homotopy type theory, including these modalities, this modal homotopy type theory, just like one might say modal logic to logic. And in the very act of doing this, it allows them to construct something they would need, like a twisted equivariant differential, non-abelian cohomology. I don't know how that fits in with that original combinatorialist in Tim's description who didn't even know about cohomology. I mean, yeah, this is a particular very fancy version of cohomology where one's mixing all sorts of ingredients, and they are being guided by this foundational language. So I was trying to weave this into an account of a sort of progress. Thomas Kuhn's anniversary centenary was last year. Where are we? Yeah, 22. Last year. So I wrote something in honor of we had a conference for the anniversary, and I wrote this article that was kind of pushing this line that we're seeing this kind of intriguing thing where the logic can shape the mathematics, which can shape the physics. Okay, but I promised you not just physics, certainly, because so if we take this list again, so something new happens, this thing that gets called applied category theory. Now, I'm somebody who doesn't think you should carve aside the applications of category theory in computer science or physics. I think they should all be seen as the same thing in a sense. But anyway, there's a field called applied category theory from about the 2010s. So, yeah, I was running a blog from 2006 with Urs Schreiber from the physics side. I mean, John Byers was the third person who started it. Again, a mathematical physicist, and they start off because they're interested in applying higher category theory to physics, to higher geometry, to higher gauge theory. Okay, but John breaks off at a certain point and thinks, well, this is strange. Look at these sorts of diagrams. There's a diagram from electrical engineering, and there's a diagram of Petri nets, maybe something to do with chemical processes. and so on, from engineering. We're seeing all these diagrams appearing in slightly different forms in these different fields. There must be something category theoretic to say about them. So that gets him very interested in this field. Okay, so something, why does category, if it does work well, why does it work well? So some important feature is this compositionality, that one builds up these bigger structures. You might be able to go back and sort of see how they were composed. They've come together by gluing together subparts of these diagrams. There's got to be a way of trying to understand how the whole thing works from the way the subparts are glued together. So there might be some operations we might want to do. We might want to take two systems and put them in parallel with each other. It's not very interesting, but we can do that. We might want to put them in series. We might make one be the input of one be the output of another. Or it might be possible also to embed a process inside another process. So I might have a process here, and then one subpart of it, I can find a process from outside and sort of plug it in a modular kind of way to the interior of that, of now that larger process. Okay, and they're doing all sorts of intriguing kinds of open Petri nets, open chemical reactions with rates, and so on and so forth. A lot of people are working on probability theory in a category theoretic way. That's very common now, and they're trying to bring all those sort of techniques from computer science, where Markov processes and graphical languages and Bayesian networks and so on and so forth. People are trying to get a category theoretic grip on that at the moment. So the cutting edge perhaps in that field, again, you can click on the links to these things. They're working on these things called stock and flow diagrams, and they've been trying to model things like epidemics. So there could be, I don't know if one can see this, we can have something to do with the susceptibility of a population to infection, something about how many people are infected, and then you could be recovered by the process of recovery and so on. Now this is the beginnings of a model. Of course, you can make this more and more complicated. And almost that's the point in a way. They're trying to get a way so that when you have a model of something like an epidemiological phenomenon, you've then got some code which will allow you to run the model. You'd love it to be the case that if somebody comes along and says, wait a minute, this bit here, there's another arrow, I need to put this other arrow in here, surely. And in fact, they've got a lovely case of this, if you click on the links, where they were presenting this in India in a village environment. They showed the model of what was going on in this health situation. And supposedly somebody came in from the street, an elderly woman came in and said, well, that's not quite right there. There's something missing. You've missed some aspect of the dynamics of our interaction. And the very act of her being able to point to this place meant that somebody could come along and sort of change that little bit of the model. And now I don't have to rewrite the code from the beginning, because it's got this compositionality structure. Okay, so that it then automatically generates the right code, and I don't have to rewrite everything. I think there's all sorts of worries, weren't there, through the period of COVID of government employees writing this very, very complicated code to model COVID, and it's very hard to see what it was doing. This is supposed to be a very transparent way of modeling situations, and it's got this sort of labor-saving device where you've got this compositionality going on. Okay, so this field just exploded, applied category theory. They have various meetings that take place through the year, and they are applying it to all these topics of causality and so on, probabilistic reasoning, learning theory, neural networks and database theory. Some shift into natural language processing, quite interesting. Consciousness would be a sort of ambitious topic, and so on and so forth. Systems biology, and so on and so forth, and quantum computing. Okay, so it's a very rich field. I've been trying to encourage philosophers for a very long time to be interested at least in category theory as a language to help them sort of think through certain kinds of concepts. So we've got some concepts very central to philosophy, like causality and so on. It feels like there should be a really important opportunity now for philosophers to come on board with this applied category theory, I think. Even if they, they should have been interested further further ago, maybe. But okay, I think my time is nearly up, I believe. Well, we can have time for questions. We can come back and fill in some details. Yeah, well, there's a bit of there seemed to be a certain kind of line of thought that this new era of applied category theory was rather separate from these other applications in, say, computer science and physics. I think that's not a good idea. I think they belong to the same family. And the work I was telling you before, by Satie and Schreiber, they're precisely trying to get at a topologically protected form of quantum computing using their kind of variety of homotopy type theory. Okay, so they right, and you can see in the construction of their quantum computing languages, they are able to embrace, to absorb within them the kinds of quantum computing languages that you're seeing, say, in the work of that Bob Kirker. Things like Quipper and these other kinds of languages are being absorbed within this larger language. I think it's not a good idea to sort of separate these two strains of applied category theory. Okay, well, let me... Now, I mean, if Alain can persuade us that maybe category theory has an application in psychoanalysis, I mean, I suppose I was intrigued, as a young man. I studied mathematics. I was perhaps, when I came to Paris, I knew that Lacan had done work in mathematics. I think I became pretty skeptical, shall we say, of the value of this application. There's lots of talk of topology and so on, and knot theory. So intrigued to find this obviously first-rate mathematician who thinks it's worth taking up the challenge again. So he's, well, I'm sure I don't need to go into the details precisely of his project. The book is appearing as a dialogue with a psychiatrist, and he's trying to kind of explain his reasons for this claim of his, linked to, I don't know, people still studying Lacan here? I don't know. Lacan has a notion of a fundamental fantasy, and Alain Kant is relating this to the idea. So a topos, as I mentioned before, that it's a category with very special properties, and one of its properties is that it behaves as though it encodes a theory within it. Okay, encodes a geometric theory. If you want the technical term, it's a classifying topos for a certain geometrical theory. Each topos is, and he's trying to relate the fundamental fantasy of an individual's unconscious through to the theory that the topos is classifying. Okay, I think you need to do quite a lot of work before one establishes that. I mean, there are other, there are even some direct links if you did want to go down this line that perhaps could be possible. There's certainly been, I mentioned in my long list of back up here, active inference. So it's a very hot topic at the moment. So this comes from Carl Friston. It's all linked to the idea that when we come to the world, we come with a lot of expectations, and essentially the world, we almost hallucinate the world, and then the world kind of corrects us somewhat. But in extreme cases, like if you suffer from delusions, the world is constraining you not at all. It's all projection. And there can be other sort of psychiatric conditions where you let the world speak too much to you. We need a balance between our kind of what we project out onto the world and the way we let the world control this. So this is the world of active inference. And there's certainly people there linking this psychoanalysis to active inference. There are quite a few people trying to do that. And as I say, there's a few people who are trying to connect active inference to category theory. So there you go. There's a path that might pass between them if that's what you wanted to do. In any case, there are plenty more opportunities. For a young person who wants to get into applying category theory, there's a world of opportunities out there. So I shall leave you with that uplifting thought that the future is bright. The future for people that want to apply category theory is bright. And I'll end it there. Thank you.